recording. And so we're recording. Let me, let's see, share screen. And that. So everybody can see the slides?
Yeah.
Excellent. And can you still see the slides?
No.
No. Okay, so this was the same issue as last time. So let's see. So you can see the slides now.
Now
So
I
let
see
me.
it.
Now you can see it. So let me see if I can put it into the full screen mode somehow. Okay, so now I'm in full screen mode, but you can't see it, right?
You're not sharing.
I'm not sharing. Okay, so now I go share that and okay. So maybe I'll just go with this. So everybody can see the screen fine, no problems?
I see it.
Okay, excellent, thank you. All right, so so the first proof, so we're going to do two proofs of the infinity of primes today. And the first one is based on the so-called Mersenne prime. So we are going to suppose that the set of primes is finite and let P be the largest prime, okay? And for our purposes, it's important that the largest prime is not 2. We need it to be an odd prime, but the largest prime is not 2 because 3 is a prime and we can verify it right here and now, okay? So it's at least 3, okay? I mean, I can't vouch for 5, but 3 for sure. All right, and so the idea behind this proof is we're going to consider Mersenne primes in quotation marks, of the form 2 to the power of p minus 1. And we claim that all the prime factors of 2 to the p minus 1 are greater than p, which instantly proves that there are infinitely many primes. Okay? So I always found this to be an incredibly elegant argument. And I still remember where I saw this argument for the first time. It was in a number theory class at the University of Chicago taught by Isaac Herstein. Now, that number theory class in Chicago did not have abstract algebra as the prerequisite. But Herstein told us on the first day that, yeah, algebra is not a prerequisite, but you really should know it. And then we asked him, what happens if we don't? And he was like, well, go to the library and learn it. It's not my problem. It was a lot of fun. And okay, so suppose that Q is a prime factor of 2 to the p minus 1. So what this means in the language of modulo arithmetic is that 2 to the p is congruent to 1 mod Q. Okay? And so what we are going to do is we are going to prove that P divides Q minus 1. And if P divides Q minus 1, in particular, P is less than Q, and we're done. So once again, what is the strategy of the argument? The strategy of the argument is we are going to assume that the set of primes is finite. We'll take the largest prime. We'll consider the so-called Mersenne prime, 2 to the p minus 1, and we are going to prove that if Q is a prime factor of 2 to the p minus 1, then in fact, Q is bigger than p, violating the assumption that p is the largest prime. So this is the strategy. Okay. So we are going to consider this set capital G, which is 1, 2 through Q minus 1. And we are going to take these numbers modulo Q. And we're going to consider multiplication of the elements of the set capital G modulo Q. Now, those people in the audience who know algebra, letter G was chosen here completely randomly. Okay.
Yeah, right.
Absolutely. Okay. And so what are we doing? We're multiplying these numbers mod q. So that means that if we take A in capital G and we take B in capital G, then to compute A times B in capital G, we just multiply A and B in the usual way, and then we find an x in G, such that AB minus x is a multiple of Q. I'm simply reminding you of how modulo arithmetic works. Okay, this is great. So we do that. And there's an interesting problem that immediately arises. Okay, if A and B is in G, can we conclude that A times B mod Q is in G? Right? We could conclude that, provided that AB doesn't equal to 0 mod Q. Right? So recall that G has 1, 2, up to Q minus 1. If you take numbers mod Q, of course, you're going to get numbers in the list 0, 1, 2, all the way up to Q minus 1. But in principle, 0 could arise. So why doesn't it? Or maybe it does. Okay? So in other words, is it possible that A times B equals 0 mod Q? Or is it possible for X to be 0 above? Remember, we took A times B, and we were looking for an X in our set capital G, so that AB minus X is a multiple of Q. And to put it yet another way, we're asking, is capital G closed under multiplication mod Q? Okay. And fortunately, this terrible, terrible possibility that AB is equal to 0 mod Q cannot happen. And who comes to the rescue? All the way back from antiquity is Euclid. Okay. In the first part of this lecture, we proved Euclid's lemma, which says that if prime Q divides A times B, then Q divides at least one of the integers A and B. But this absolutely cannot happen, okay? Because A and B are between 1 and Q minus 1, okay? And so we've used the fact that Q is a prime, and we have used the way we arranged the elements of G. Okay, so we have just shown that this set capital G, consisting of 1, 2, all the way up to Q minus 1, in other words, consisting of all the representatives mod Q, if you will, except for 0, is closed under multiplication mod Q. Okay? But the story doesn't end there. Not only is this set closed under multiplication, it has other wonderful features that one might hope to find when multiplication is involved. So we are going to see in a moment that every element of capital G has a multiplicative inverse mod Q. In other words, for every A in capital G, there exists a B in capital G, such that AB is congruent to 1 mod Q. Okay? And what are we going to do? We're going to search. So we are looking for a multiplicative inverse of A modulo Q. So what are we going to do? We are going to search for it in the most aggressive possible way. So what are we going to do? We're going to take A. Well, if A is already equal to 1, then we're done. Then we're going to take 2 times A. If that works, we're done. Otherwise, we continue 3 times A, all the way up to Q minus 1 times A. Okay? So, okay, this approach is aggressive, but why does it work? How do we know that one of these elements is indeed 1? Okay? multiplication modulo Q? Well, the first thing we do is we count the elements. So this is 1, 2, 3. So how many elements are there? Q minus 1. Okay. We know that none of them are 0. So a question that inevitably comes up is, can these elements repeat? In other words, are they all distinct? Okay. Imagine for a moment that you could show that they were all distinct. Well, if you have Q minus 1 elements here, remember we're going mod Q. 0 is not in the list. 0 is not in the list. So if these elements don't repeat, 1 has to be there. It simply has no choice. Because 0 is not there, and there are Q minus 1 elements, possible elements left. So if all of these are distinct, then 1 must be in the list. So why can't they repeat? Well, once again, suppose that they do, then NA equals MA mod Q. And without loss of generality, N is bigger than M. Okay? But what does that mean? That means that subtracting, we see that N minus M times A is a multiple of Q. But this is once again impossible by Euclid's lemma, because if N minus A is a multiple of Q, then either Q divides A or Q divides N minus M, and neither of these is possible. Okay, because they're all smaller than Q. So what have we just shown? We have just shown that this list of numbers that we wrote down is of size Q minus 1. 0 is not there, and all of the elements are distinct, which means that 1 must be somewhere in this list. And so that means that there's some N, so that N times A equals 1, and that N is the inverse. So fantastic. So this set capital G is a gift that keeps on giving. First, we found that it's closed under multiplication mod Q. Then we found that in fact multiplicative inverses exist. And the question is, what does that do for us? Okay. So let's go back to this problem of Mersenne primes. So remember, we have assumed that P is the largest prime in the world, and that Q divides 2 to the P minus 1. Remember, the goal is to show that Q is bigger than P, because if Q is bigger than P, then P cannot be the largest prime. Okay? So what does it mean that Q divides 2 to the P minus 1? What it means is that 2 to the P corresponds to the element 1 in capital G, which is 1, 2, all the way up to Q minus 1, taken mod Q. Okay? And what this tells us is that we should probably be looking at the set capital H, which is equal to 1, 2, 2 squared, all the way up to 2 to the P minus 1 mod Q. Okay? Because it certainly looks reasonable to suppose that the resolution of this problem lies in understanding the properties of this set as they relate to the properties of the set capital G. Okay, well, let's play around with this set for a few minutes. First of all, what is the size of capital H? It seems to have P elements, but perhaps there are repeats. Where have we seen this movie before? It seems that somewhere we have seen this movie, right? So suppose that 2 to the A is equal to 2 to the B mod Q, where A is bigger than B. Okay, so what does that do? So dividing, it means that 2 to the A minus B is equal to 1 mod Q. Remember, we have shown that every element of capital G has an inverse, okay? And so what happens here? 2 to the power of A minus B is 1 mod Q. So let's write P as a multiple of A minus B, say U1, plus a remainder. But this remainder is at least 0 and at most A minus B, okay? Since P is prime. And now what we are going to do is raise 2 to the power of both sides. So 2 to the P is 1 modulo Q. 2 to the power of A minus B is allegedly also 1 modulo Q. So what does that mean? What this tells us is that mod Q, we have 1 equals 2 to the P, 2 to the power of V1. Okay? And remember that this V1 is smaller than A minus B. Okay? Well, we can keep playing this game over and over and over, and we will eventually come to a very sad conclusion that 2 equals 1. And this is just not true. Okay? So it follows that all the elements of capital H are distinct. Okay? But is capital H closed under multiplication mod Q? So we know that if we take any two elements of capital G, then you get an element of capital G because you cannot get 0. But what about elements of capital H? Well, the product of 2 powers of 2 is certainly a power of 2, so there's no problem there. But the question is, can a product of 2 powers of 2 be 0? But we know that this cannot happen because capital H is a subset of capital G. And we already showed that this is impossible for elements of capital G. It is impossible to multiply 2 elements of capital G and get 0. Okay? All right, let's continue. So let's summarize what we have up to this point. We are trying to show that if P is the largest prime, and we consider the number 2 to the P minus 1, and Q is its largest, and Q is its prime divisor, then we want to show that Q is bigger than P, violating the assumption that P is the largest prime. Okay? So for that purpose, we constructed a set capital G, which is the set of numbers 1, 2, all the way up to Q minus 1. Okay? We showed that it's closed under multiplication mod Q. And we showed that every element has an inverse, multiplicative inverse mod Q. Okay? So similarly, we have a set capital H, okay? Because we're looking at 2 to the P being congruent to 1 mod Q, because this is what it means for Q to divide 2 to the P minus 1. Okay? So we're now looking at the set capital H, which, just to remind you of the definition, consists of powers of 2. 1, 2, 2 squared, all the way up to 2 to the P minus 1 mod Q. And by basically the same arguments, we were able to see that this set is also closed under multiplication mod Q. and every element of the set has an inverse that also lives inside the set. Okay? So now the name of the slide is Rolling Begins. We're going to show that we can roll capital H into G. Okay, so what does that mean? Now, if you take an arbitrary set of capital G elements, okay, then if you take an arbitrary set of Q minus 1 elements, there's absolutely no reason why the size of a subset should divide Q minus 1. Okay, there's absolutely no reason for that. But capital G is not just any set. It has structure that we just exhibited, modulo Q. It is closed under multiplications mod Q. And every element has a multiplicative inverse mod Q. And capital H also has these properties. And we're going to see in a moment that the presence of these algebraic properties is extremely powerful. Okay? All right, so how do we exploit the fact that these sets have this structure that we have just exhibited? Okay. Okay. So I promised to roll capital H into capital G. So this is the rolling pin. This is what we are going to use. Okay. Everybody has one under their desk? Yes. Okay. Fantastic. And okay, so rolling pin in action. Okay. Once again, capital H is 1, 2, so 2 to the p minus 1. And capital G is, oh, capital G begins at 1. There's a theorem that there must be a typo in every set of nodes, and there it is. Okay, so this is 1 through Q minus 1. There is no 0. Okay. And we want to show that P divides Q minus 1. Okay, so let's begin with the observation. Okay, let's begin with the observation that that if capital H equals capital G, then P equals Q minus 1, and we're done. Okay. If not, then there must exist an X in G, which is not an H. Okay. And what do? We're going to consider capital H times X, which is X, 2X, all the way up to 2 to the power of P minus 1 times X. So we are going to multiply X on the left, although it doesn't really matter, by every element of capital H. Okay, mod Q. So what happens if we do that? Okay, so one interesting question is it possible for HX to intersect H? And why is this an interesting question? Well, suppose that H and HX between them filled up all of capital G. And suppose that magically capital H and capital HX did not intersect. Well, we know that the size of capital H is P. We know that the size of capital HX is P for the same reason. Okay. And so then it would follow that 2P equals Q minus 1. And once again, this would mean that P divides Q minus 1. Okay, so it would be useful to know that HX doesn't intersect H. But why is that? Let's take a look. Suppose that capital HX intersects capital H. What this means is that there are some elements H1, H2 of capital H, so that H1X is equal to H2 mod Q. Okay? Well, we know they're inverses, so we multiply both sides on the left by H1 inverse, and we see that X is equal to H1 inverse H2 mod Q. Okay? But we also know that H is closed under multiplication, and every element has an inverse. So this implies, in fact, that X is an element of capital H. But X is not an element of capital H. This is how X was chosen. Okay? So this implies that HX and H cannot intersect. Okay? So once again, just to go over the logic, if H union HX is G, then since they do not intersect, 2P equals Q minus 1. And we're done, since this would mean that P divides Q minus 1. Okay? Well, suppose this doesn't happen. What do? If this doesn't happen, then there exists a Y in G such that Y is not an H and Y is not an HX. Okay? And by the exact same argument as the one we discussed, HY does not intersect H, and it does not intersect HX. Okay? And so now if the union of capital H union HX union HY equals capital G, then Q minus 1 equals 3P, and we are once again done. Now we could do this for a while. The question is, why does this process terminate? This process terminates because Q is a finite number. So the set capital G has Q minus 1 elements, which means that this process has to terminate after a finite number of steps. Okay? So the rolling process will end, and in the end, we will see that capital G is equal to H union HX1 union HX2 all the way up to the union HXN, where XJ is in G, okay? And HXI intersect HXJ is the empty set if I doesn't equal to J. Okay? This is done simply by continuing the process that we described in exactly the same way. And then it follows that Q minus 1 is again a multiple of P, so P divides Q minus 1 as desired. So we're now ready to summarize this argument and draw conclusions. So what have we done? We assumed that P is the largest prime, and we considered the number 2 to the P minus 1. Okay? We then showed that if Q is a prime that divides 2 to the P minus 1, then in fact P divides Q minus 1, which forces P to be smaller than Q. Okay? And this shows that P is not the largest prime, which yields a contradiction. Okay? Now, so for those of you who have seen group theory before, you can of course see how quick and elegant this argument becomes once group theory is something that is in your possession. For those of you who have not seen group theory before, what I'm very much hoping is that this will spur you to look up on Wikipedia what group theory is and go from there. Okay, because it's a truly, truly beautiful subject. All right, and as always, if you want any suggestions on books to read in any particular direction that arises during these lectures, or even those that don't, please let me know. I'm always happy to talk about it. Okay, so this is the Mersenne prime proof of the infinity of primes. And now we almost completely switch gears, and we are going to give another proof of the infinity of primes, which is of fundamentally different nature. Okay, and so the harmonic series are back. So in the second lecture of the basic skills segment of the coronavirus lecture series, we showed that the partial sums of 1 over k, so if you take summation of 1 over k from k equals 1 to capital N, that this tends to infinity as capital N goes to infinity. So these partial sums grow, and as we described in that lecture, this means that the summation from k equals 1 to infinity of 1 over k diverges. Okay, so if there's anybody here who was not present at that lecture, both the file and the video of that lecture is on the website for this series. But we proved a lot more than that. Okay, we gave a very quantitative argument which showed that, which implies very quickly that if x is a positive real number, let's say bigger than 1, and x is bigger than or equal to an integer n and less than integer n plus 1, then log base 2 of x, in fact, it's true for the natural log of x, but I decided to go with log base 2 because it's a slightly easier quantity to handle in some ways, is less than or equal to 1 plus 1/2 plus 1 over n. In other words, the partial sum of the harmonic series up to little n. Okay? And what we are going to do now is we are going to take advantage of this calculus fact. Well, we didn't use any calculus in its derivation, but let's say we're going to take advantage of this analytic fact to derive the fact that there are infinitely many primes. Okay, so what do? We will start out by observing that if you take 1 plus 1/2 all the way up to 1 over n, okay, then this is certainly less than or equal to summation of 1 over m when m is in the set of positive integers which only have prime divisors that are less than or equal to x. Okay, and okay, so this is pretty clear. And in our previous lecture, we proved that every integer has a unique prime factorization. And this fact has the following really, I think, amazing manifestation. Okay, so let's sort of stare at this for a second and make sure we understand how this works. So I claim that if you take a sum of 1 over m, where m ranges over positive integers which only have prime divisors less than or equal to x, then this is equals a product over primes less than or equal to x of the summation over k bigger than or equal to 0 of 1 over p to the k. Okay? Now, at the first glance, this looks complicated. It is not. So what is this sum here? You pick a prime p, and then you have 1 plus 1 over p plus 1 over p squared, and so on. Okay? Okay, now it terminates because we're only considering primes less than or equal to x. Then you choose a different prime. And you again write out 1 plus 1 over p plus 1 over p squared, and so on. And you do this for every prime less than or equal to x, in accordance with what happens on the left-hand side. When you multiply out all these expressions, in the denominators, you will get all the possible prime factorizations. Because in each of these strings, in each of these sums, you'll get 1 over a prime to whatever power you wish. And then when you multiply it by the next set of parentheses, you can again multiply it by 1 over another prime to whatever power you wish. And this way you'll go through all the primes, well, not all the primes, but all the relevant primes, because we only care about primes less than or equal to x. Okay? So in fact, summation of 1 over m, where the sum is over all the positive integers, where the prime factors are less than or equal to x, is equal to this absolutely beautiful expression. Okay, I believe that this argument is due to Euler, but I'm not sure. Okay, so this is a product over p prime, p less than or equal to x, and then you have a summation over k bigger than or equal to 0 of 1 over p to the k. So let's just think about this and let's anticipate it, right? So it's a beautiful formula. Beautiful formulas are great, but what is this going to do for us, right? Why is this a useful expression that will eventually lead us to be able to conclude that there are infinitely many primes? Well, let's maybe not think this far. Let's just see why this is an expression we can work with. Well, one of the reasons is that this summation over k bigger than or equal to 0 of 1 over p to the k is not just any series, it's a geometric series. And for an infinite geometric series, we have a simple formula, which we derived in one of the previous basic skills series lectures. Okay? So this sum, we will be able to evaluate exactly. Okay? And so this gives us hope that we can obtain an expression that we can work with. Okay? So let's go ahead and execute this. So the inner sum is a geometric series, and we have a summation from k equals 0 to infinity of 1 over p to the k, which is of course the same as the summation from k equals 0 to infinity of 1 over p quantity to the k. So this is just equal to 1 over 1 minus 1 over p, in accordance with the formula for the geometric series that we derived. Okay? And so it follows that log base 2 of x, and in fact, you can replace log base 2 by the natural log, but that doesn't change anything. This is less than or equal to the product over all the primes less than or equal to x of 1 over 1 minus 1 over p. Okay? And simply rewriting the algebra, this is the product over all the primes less than or equal to x of p over p minus 1. Okay? And there's something amazing about this product, right? So during the second basic skills lecture on sums, we discussed how useful it is to have telescoping sums when the subsequent terms cancel the terms before. Okay? Well, what we have here is a telescoping product. So let me explain. Okay? So first, let's put this into wider context and bring ourselves a tiny bit closer to the goal, which is to show that there are infinitely many prime. So given x bigger than 2, say for now, let pi of x be the counting function for the prime numbers. So this is the number of primes that are less than or equal to x. Okay? So what do we have? So in this language, log base 2 of x is less than or equal to the product over primes less than or equal to x of p over p minus 1. And this is a product from k equals 1 to pi of x. Remember, pi of x is the number of primes less than or equal to x of the kth prime, p sub k, over p sub k minus 1. Okay? And so let's note that since not every integer is prime, there are many wonderful jokes about that, as you know. P sub k is bigger than or equal to k plus 1. Okay? This is an incredibly weak statement, but amazingly, in conjunction with everything else we have, this is going to be enough. Okay? So look at what happens here. So we have P1 over P1 minus 1, right? And then you keep multiplying it, right? Then you okay, so let's rewrite it first. Okay, so using the above, what do we have? That log base 2 of x is less than or equal to the product from k equals 1 to pi of x of pk over pk minus 1. And now what we need to notice is that the function t over t plus 1 is a decreasing function. So as t gets larger and larger, t over t plus 1 gets smaller and smaller. Okay? And this you can check by brute force. You can simply check that as you increase the value, this function decreases by doing the algebra. All right? And remember, I was sort of foreshadowing that it would be nice to set up a scenario where you have a telescoping product. And we are finally there, right? Because what happens here? This is k plus 1 over k. So when k equals 1, you get 2 over 1. Then when k equals 2, you have 3 over 2. And then 4 over 3. And the very last term is pi of x plus 1 over pi of x. So the 2's here cancel. Then the 3's cancel. Then the 4. And the only thing that is left in the end is pi of x plus 1. Okay? So just look at this over here. What we just showed is that log base 2 of x is less than or equal to pi of x plus 1. In other words, the number of primes that are less than or equal to x is at least as large as log base 2 of x minus 1. And in particular, as x gets larger and larger, pi of x gets larger and larger, which establishes the infinity of primes. Okay, so the telescope
Excuse
is
me,
back.
Alex,
Yes.
could I
Please?
ask a question? Can you go back to that previous slide? What do
Sure.
you mean when you say that? What do you mean when you say the function t to t, that function is decreasing? It seems to me that as t increases, the value of the function gets closer and closer to 1. It's an increasing function.
Okay, 1 second. Let me make sure.
Maybe I misunderstand what you mean.
No, let's see, t over t plus 1. So 1 second, let me, so, oh, no, I am sorry. It is flipped. It is t plus 1 over t.
Okay.
It is
Okay.
t plus 1 over t. So this is a typo, right? This is t plus 1 over
Okay.
t. T plus 1 over t is indeed a decreasing function. And this is what we are using to make this inequality. So thank you
Okay.
very much, Doug. You're absolutely right that this statement is incorrect. Fortunately, this statement is correct because the relevant function is not t over t plus 1, but rather the function t plus 1 over t.
Okay.
But thank you very much for pointing that out. And that does allow us to conclude that log base 2 of x is less than or equal to the product from k equals 1 to pi of x of k plus 1 over k. And then we work through the telescoping product, and we conclude that pi of x is at least as large as log base 2 of x minus 1. Okay? And okay, this is the telescope. So not only does this argument show that there are infinitely many primes, it in fact shows that the counting function grows at least as fast as the logarithm function, okay? And so this is sort of a first step in the direction of not just showing that there are infinitely many primes, but in the direction of trying to understand how many primes are there in the given range, okay? And in one of the future lectures, I'm going to prove a result due to Chebyshev, which says that there exist constants little c and capital C, such that the number of primes less than or equal to x is bounded above and below by constant multiples of x over log x, okay? And here log x denotes the natural logarithm, but since the constants are not specified, it doesn't much matter what the base of the logarithm is. And let me finish up this lecture by what I call a quick glimpse into deep waters. So one of the central results in mathematics is a prime number theorem, which was proved in 1896 independently by Jacques Hadamard and de la Vallée-Poisson. And it says that in fact, pi of x is equal to x over log x plus smaller terms. Smaller terms, I mean terms that are much smaller than x over log x, without writing out technical statements for now, okay? But to dive into even deeper waters, so this result is wonderful, it is not easy, but it's known. To dive into even deeper waters, what is the Riemann hypothesis? So the formulation of the Riemann hypothesis that most people hear about is the one in terms of zeros of this object called the Riemann zeta function. But my favorite formulation, or more precisely, my second most favorite formulation, my favorite formulation will come up eventually in this lecture series. But my second favorite formulation says that the number of primes less than or equal to x is equal to x over log x, but this time it's not just terms smaller than x over log x. It is terms smaller than a constant times x to the power of 1/2 plus a tiny bit, okay? And let me not be terribly precise about what I mean by this tiny bit for the purposes of this lecture. So just think of it as showing that the error is not just smaller than x over log x, but showing that it's smaller than something that's pretty close to square root of x, okay? And the reason I wanted to illustrate this is because in the context of prime numbers, it is incredibly easy to go in just a few steps from problems that are widely accessible and that are not difficult to understand to problems that nobody has any idea how to even approach, okay? And I think I'm going to stop there. you very much. Are there any questions?
Mhm.
Oh, hello, Fatma. Didn't see you.
Hi, Alex. How are you?
Fantastic, fantastic. Really good to see you. It's been a while.
Yeah.
Okay. So if there are no more questions, what I'm going to do is I'm going to correct those 2 typos that you guys found. So thank you very much. And I'll correct those typos and post it on the coronavirus lecture series website. And thank you all very much. And so just want to tell you that next Thursday, A.V. Powelson, who is a former visiting assistant professor at the University of Rochester and now a professor at Virginia Tech University, is going to give a lecture in this lecture series on the Erdős distance problem. I think it's a really, really beautiful subject, and I very much hope to see you there. Okay. Okay, so thank you very much. And
Wait, one more thing.
yes, please, go ahead.
This is completely unrelated to the lecture, but when are you available to meet about what we discussed earlier?
I will write you an email right after this, but there'll be no problem.
Thank you.
Okay, sure. Okay, thank you all very much. Have a wonderful evening, and thanks for coming. Bye-bye.
Thank you.
Thank you, Alex.
Bye.
That was fun. Good job.